Looks like Mr. Archer, he's having network issues and can't make it, so you get the lab from me. Lucky y'all. I'm tidying up my desktop so I can actually present the lab.
Soccer 120. Oh, I knew it too. I knew it too. What a shame. I'm gonna play A this time.
All six of y'all. So here we go.
Play retake A.
Chat over there.
Josh got out early.
I'm actually going to work on my home server. So this is lab 26. And what you guys get to is you go this way. So there is the lab HTML file, and there's the internal link, and you know it's correct because it's got the right URL, and then you would download that, and if you download it, you have this. Make a quick change. I want to work on a copy. So I'm now working on a copy of the lab. Why do I choose to do that? Because here's questions you can actually answer. In the chat box, we'll render an opinion on why to work on a copy. That's so if I screw stuff up, I don't wreck the original. All right, the first part goes into some discussion of prediction engines and regression. This is from prior versions of this class. It kind of doesn't really fit in today's topics in any great way. Essentially, it's saying that our brains are pretty good at recognizing patterns, and the regressions we're going to perform today is a type of pattern recognition algorithm. And the way we do that is by guessing or predicting the next step based on information that we've obtained from the prior steps. So if you recall our famous time and speed model, we can build and plot that. And remember, we kind of arbitrarily made up values for M and B and tried to make it our best possible fit. Linear regression is a predictive analysis technique that uses observed data to predict an output variable. Actually, what it's trying to do is create an equation that represents the data. The predictor variable, in this case, is the variable that predicts the output. Typically, it's referred to as X, but it doesn't have to be. And the output variable is what we want to predict. It's typically referred to as Y, but again, it doesn't have to be. If we're using linear regression, which is the topic of this lab, we are stipulating the equation y sub b, which means our estimated value of y is equal to b times x plus alpha, where alpha is the intercept and b is the slope, or y sub b is the estimated or predicted value. A meaningful goal is for us to find statistically significant values of the parameters alpha and beta that minimize the difference between y sub 0, which are the observed y's, and y sub b, which are the predicted ones, and to find an optimum value of those parameters, and that's the best we can do. So here we have a blue line passing through red dots, and we have these green vertical bars that represent distances between the model, blue line, and the observations, red dots. And by shifting the blue line left, right, up, down, and changing its slope, we can reduce the length of those green bars to some point where we can't make them all collectively any shorter, and that's our best fit. The equation that does that was called the normal equation. It was presented in the lesson, and the slope is equal to the sum of the observed values of x's minus their mean, multiplied by the observed values of y minus their mean, divided by, so this first part is like a standard deviation of the x's, standard deviation of the y's. The second part is the x's minus their mean quantity squared, so that's like a variance. That gives us the slope. Correlation coefficient divided by variance is slope. And then our intercept is the average value of y minus b times the average value of x. So our covariance formula is shown here in the picture. And the covariance is useful for constructing these normal equations. The correlation coefficient is literally a covariance formula divided by a normalization process. And we had Pearson's R earlier in the class. And if we take our original example, we can create the data frame as we've done before. Actually, let me run that, I might need it. Describe it. And now we're going to get the variance of time and the variance of speed. We will report those two back to ourselves. We can get our covariance matrix. So we see time versus time has a covariance of 11, and speed versus speed has a covariance of 1697. Those magnitudes simply mean that the values of the two things are quite a bit different. What is important, however, is time and speed has a positive and fairly substantial covariance associated with it. So time indeed might be a good predictor of speed. If these numbers were small, that would imply that there's very little information about speed confirmed with knowing time, and vice versa. So to find the correlation among columns, we can use the Pearson's method. And now we have basically normalized the covariances. And so time associates with itself perfectly as it should, speed with itself perfectly as it should, and more importantly for our examination here, time is a pretty good predictor of speed. These correlation coefficients are pretty close to 1. So positively correlated and close to 1, time's a good speed predictor. So now we'll do linear regression using very primitive Python. We simply get the mean value of time, the mean value of speed, and we take that mean and subtract it from time, take the speed mean and subtract it from speed, create a matrix called the variance, which is time minus its mean quantity squared, and then we can calculate our slope and intercept from that information. The slope is simply the covariance of the two variables x and y divided by the variance of x, and the intercept is the mean value of y minus the mean value of x times our just computed slope, and we'll print those two. Now we have an estimate for x and beta, alpha and beta. We can produce our predictions, and let's plot our results. And there is our red line, simply based on computed variances and computed means of our observation. It's not bad, but there's easier ways to do it. So a better way to do it might be to use the stats model package. And the stats model package has a function called ordinary least squares built in it. And the attractiveness of stats model is the fairly simple way of defining linear models using something called a model logic constructor syntax. And so this expression here, speed tilde time, we're instructing the package, create a model that predicts speed based on some linear combination of time and some constant. And we don't have to do the calculations ourselves. If we had other variables, we can simply put them in a list like that. And that is an attractiveness of this particular application programming interface. Let me return it to the way that will actually work, because other names and other names too don't exist. And in the function call, we have the name of the object. We have the model we want it to attempt to fit, and then we have to tell it where the data are contained. And here we have a rather weird looking syntax that says data equals data. And that's because up here we named our data frame data. So somebody in the chat box come up with a better name than data. How about Captain Picard? Don't like Picard as a name. If you don't like the character, so we do that. That didn't hurt anything. We describe data, it will be messed up. And so now to use this model, we would simply change this to Picard. So that was a very important point I just made. Did the 6 of you all that are watching actually get what was going on there? Yes, no question. Awkward silence. Well, then moving on. By putting Picard there, we can go ahead and good, it ran. Recover the parameters. We get the intercept and the time. And now we can make a plot. And there is our model using the statistics package. So there's a question here. It says, how good do you feel about this predictive model? Will you trust it? That's something you will need to answer. Okay, since we're here on the stats package, we can play some useful games. Let's add a new column of Times Square. This is our New York version, and that is so this is going to square the time column and put it into a new column in our data frame. We'll run that. And now let's modify our fit. We'll play a different game in a minute. So we do that, you claim to run. Now we have intercept, value for time square. And let's see, data speed. Yeah, I think this will plot. And now, ask the question, how do you feel about that predictive model? So which predictive model do you like better? I wonder if I have my audio turned off. I don't think I do. I'll leave you all to. Chris G likes this one. I do too. That's clearly at least for going from 0 to 10, that is a much better visible fit than the original model. Now, what I like about the stats model package is we didn't necessarily have to do time squared that way. I think we can actually do it directly in the API. We'll know in a second. Oh, maybe not. I could be wrong. I am wrong. These other objects have to already exist. So had I not done that, I would never know. All right, let's look at a second example. We're going to look at a classical regression problem where we have a data set of how much money we spend on television, radio, and newspaper advertisements, and the number of sales for a particular product. So we're selling meal kits. So we're advertising on TV, radio, and newspaper. And our goal as salespeople, as Amazon, is to make as much other people's money ours as possible. Unfortunately, we have to spend money to do that. We can't just show up with armed robbers and take people's money. It doesn't work that way yet. And we want to ask ourselves a series of legitimate business questions. And these could be engineering questions. So we could be in engineering sales, selling engineering services. And we want to know, does television advertising give us the ability to predict sales for a product? Does radio advertising predict sales? Does newspaper advertising predict sales? Can we use all three of them to predict sales? That's called multiple linear regression. We're going to study that more in the near future. And then of the three, which one is the better predictor of sales of the product? So naturally, the first thing we have to do is obtain the database. So the scripting is here to allow us to get the database. I'll go ahead and run that. And let's be sure it actually pulled in a database. So the database should look like that. A column for television, radio, newspaper, and then the sales. And I actually don't remember the scale of these. So for lack of anything else, we'll just consider these to be dollars and thousands of dollars. Now that we have obtained our database, the next thing to do is to read it into a data frame and examine the data frame. So our data frame has television, radio, newspaper, and sales. So we have TV spending, radio spending, newspaper spending, and then sales for those different conditions. And we can do a tail function. There are 200 entries in our database. I guess we could have got that from the next function, which is described. We can describe the data frame, and it tells us that in the television column, there's 200 objects, radio 200, newspaper 200, sales 200. The mean value of TV is 147. The mean value of radio is 23. Mean of newspaper is 30. The standard deviations, 85, 14, 21 respectively. The minimum value and the maximum value and the maximum sales value. So let's go ahead and we'll create some NumPy arrays from the data frames, and that's to allow us to do our variance and covariance calculations the way we know how. So we'll create an object called TV, radio, newspaper, and I guess we should call this one sales because it'll work better. And now get the variance and covariance. First, from our data frame, the variance of TV is 7,300, radio 220, newspaper 470, and sales 27. And then we have the covariances of the different things. But variances and covariances are difficult to interpret just by looking at them. So instead, we're going to get the correlation coefficient matrix. We do that by running the correlation method on Pearson. And it's now telling us that TV is perfectly correlated with itself, as it should be. Radio is perfectly correlated with itself, as it should be. Newspapers are perfectly correlated with itself, as it should be. Sales are also correlated with itself. But more importantly, television has a pretty high correlation coefficient with sales. Radio, less high. Newspaper, less high still. And we can use that to help answer the first question. Can television advertising spending predict the number of sales for the product? As a regression question, that is simply, let's regress sales on TV spending and see what we learn. If we do that, we find out that the intercept is 7 and the slope is pretty small. If we go ahead and plot that, we get the following, and as predictor models go, it is indeed predicting a trend that as we get larger in our TV spending, our sales goes up. But look at this bottom envelope here. As we're moving along the bottom, it's quite possible to spend a lot on television advertising, and the difference in sales between almost 300 units of spending and 50 units of spending is pretty small. And the other thing that we're seeing is in the spread of the observation dots, it looks kind of like a horn. As it's getting bigger as we move to the larger thing, that's called heteroskedasticity. It means the variance is different depending on where we are in the spending axis. So I would go ahead and postulate that we don't have a very good predictive tool as of yet. Let's try that again with radio. If we do it with radio, we see somewhat similar behavior, a little bit less heteroskedasticity. The red line's implying that there is some relationship between radio advertising and sales. But if we look over here at the left, when we're very close to zero radio, we have a certain number of sales, and that is well within the range of the observed values here at the right. Lastly, we can play the same game with newspapers. Again, we're just operating our bidding process, run the model, predict the values. And this one is actually the worst of the three. That red line is nearly flat. So if the slope goes to 0, what that's telling us is there's absolutely no predictive values of spending on sales. The best you can do is just use the average value of sales to go forward. Another tool is called the sklearn package. In some cases, you may actually have to install it, and we'll see if it's installed on mine. Oh, cool, looks like it is. We're going to use a tool in the sklearn package called linear regression. Now, the linear regression tool is doing the same kind of thing. But the difference is how we set up the prediction matrix and the design matrix. In our prediction matrix, we're going to create a list called predictors. We're going to tell it to use television, radio, and newspaper. And then we'll take our data frame, we'll supply it with predictor list, and we're going to supply that to another data frame called CapX, which is what I've called the design matrix. So we actually explicitly build the design matrix. And then our prediction data frame is what we're predicting, in this case, sales, and we take it directly from the data frame. Then we will initialize and fit the model. So we're going to apply linear regression. We're going to store its results in an object called LM. And in the LM object, we're going to apply the fit method. And we're going to fit Y using CapX. And we'll assign that result to an object called model. And then we will print the alpha and beta, the intercept, and the coefficient. Now notice these particular print functions. That's unusual compared to what you've seen so far. What is that leading F in the print function doing? Awkward pause. What it's doing is, in these curly brackets, that's a replacement object. So alpha equals whatever's in the curly brackets, and we want to print it as a floating point variable. We could do something like, remember the syntax, see what that does. I have the syntax incorrect, so it's F.2. Well, if we forget the syntax, the way to do is go off to the mighty internet and let's see. F strings in Python, literal string interpolation. So we proceed with the letter F. Oh, the rounding actually has to be done at the method level. My bad. Oops. We'll leave that again. We'll leave that alone. I think I do it this way. There we go. That's how to embed the expression directly into the string. So here's our model, and in this case, we're running the multiple predictor model. So we've done multiple regression. So we have an intercept, a slope associated with television, a slope associated with radio, and a slope associated with newspaper. And we're actually trying to fit that sales is equal to alpha plus B1 times TV plus B2 times radio plus B3 times newspaper. If we do that, we see that the contribution of television is 0.04 multiplied with whatever scale the TV costs are. Contribution of radio is 0.18. Contribution of newspapers is negative 0.001. So newspapers are almost useless. Television is close to useless. The only thing that is arguably usable is our radio. I'm going to turn off my warning suppression so we get to see the warnings. And now we will plug this into our prediction tool. And we get some warnings. And now we answer the final question, which is which parameter is a better predictor of the number of sales for the product. At this point, we might actually want to produce a plot. So we'll grab our data here, our script here. Let's see, model.predict works.
Actually, this is the wrong kind of plot. I'm just going to delete it. Never mind. So answer the final question. Which parameter is a better predictor of the number of sales for the product? How do we answer that? What do we infer from the betas? Again, that will be left for you all to do. The answer in the question is the last one. What can we infer from the betas? All right, so the SK-learn example we just did is a example of something called multiple regression. And we're going to study that more in the coming few lessons. We can use that to improve our time speed example. So remember our time speed example, first we make sure the data frame still exists, which it looks like it does. And let's suppose we use SK-learn to do a linear fit. We do that, there's our fit. At this point, so what? Here we're going to add an additional column to the data frame called time squared. So we've made that. Now we have this new column, and we'll modify our model a bit. So we extend our predictor list to include time and time squared. Put that into the design matrix. We're going to predict feed and then run the fit. And then ask you again which model you prefer. Based on our last implementation of this particular approach, everyone liked this curvy one. But let's actually have a little more fun. Let's introduce a cubic variant. Time cube. Sounds like something from Doctor Who. Now, how do I cube something? You times it by itself 3 times. Now we have time cube. We can add that to the list. Refit. And in this case, X has 2 features. There we go. There's no mistake right there. That's better. Adding our cubic term probably wasn't very useful. Let's see what the parameters are. Those come out of the back here. So I think the one on the cubic is going to be close to what number? So we have a intercept, and we have a model coefficient associated with time, a model coefficient associated with time squared, and a model coefficient associated with time cubed. So for all the bragging rights this afternoon, what is your best guess of the model coefficient associated with time cubed? You all can make the guess if you're still listening. If you're just recording it and hoping you get credit for being here, so be it. How many of you all are left? 1, 2, 3, 4, 5. So I think it's going to be 0. Sure enough, pretty darn close to 0. So that has also helped you understand how to answer this question up here. Not that one, this question, whatever it is. That question right there. All right, so how did this validity change work? Well, if we go back to our prediction response model, we essentially are messing with a polynomial model. And one way is to construct a design matrix. All we did when we added those new predictors is we populated this column, the rightmost column in the design matrix, added a variable, and in our Y matrix, which here is typesetting incorrectly, I'm going to fix that because that's going to drive me nuts. There's how it's supposed to be. To find the unknown beta values, all we did was solve this linear system, which we already know from today's lecture is the system that minimizes something. And if anyone wants to type in the chat box what it minimizes, you get all sorts of Amazon gift cards or the Amazon.com, the Mars outlet. Once the values for beta are obtained, we can apply our plotting tools. And so all we did up here was added an x squared and x cubed column. And if we were doing that into the primitive Python, we'll just run this one. This is the x squared version. And we get that. And if we want to add a third one, we would have to add numpy dot array time qubit. Shape is correct, response is correct, x transpose. We need the third value here. Cube that, gives us a polynomial back. Model back, and I believe that will let us run a cubic. Polynomial is missing one positional argument. Zero, B1, B2. Nope, it's not. I'm just missing an argument. Yeah, it's thinking all right. So I have one more right down here. There it is. So there's with our polynomial model, not much change. And again, that is because the value of beta is quite small. I think I got that right. So the value on time is, excuse me, the intercept is 0.5, the value on time is 0.7, the value on time squared is 1, the value on time cubed is 0.008. All right, the exercise, we got about 12 minutes to go. And here we're going to use these ideas to determine if the cost of tuition translates into higher paying jobs. So we have a database that's going to list 10 colleges and the post-graduation salary for 10 years after graduation and the annual tuition cost. We're instructed to build and fit a linear data model, determine which variable is the predictor, which is the response, and does the resulting model suggest that tuition paid predicts post-graduation salary? Or a more important question is it worth spending a bunch of money to get more higher paying job later on? So first we have to get the database, and that's already been coded here. So I'm just gonna go ahead and download it, make sure that we actually got it. So here's our school: Princeton, Harvey Mudd, Caltech, Naval Academy, United States Military Academy, MIT, KEY, MOUSE, Lehigh, and so on. Babson College. I wonder if that's supposed to be Boston College. Huh. And we have the 10-year salary. So, for example, graduates of Princeton 10 years afterwards are earning on average $137,000, and they paid $28,540. The two military academies are a bit tricky because technically there's no tuition, but you do pay for them. So let's return to our copy. So now that we have the data, how do you read it into a data frame? So like Josh, I'll wait till somebody types something in the chat to tell me how to read it to a data frame. Plus, I would scroll up to find out if I've been in somewhere else, so I don't have to rethink it. So we have a way to read like this. So we go ahead and copy that, paste it. I notice that many people can handle copying and pasting, which is perfect because it saves us from having to think. What do we want to name this data frame? Somebody suggest a name. This one it is. And what are we reading? We're reading school to salary .csv. Pandas should already be loaded, so I don't like that data frame. STS, that's 2S. Okay, how do we know if we read the data frame? You can look at the head. And sure enough, it looks like we have the data frame. Now we have to make a scatter plot. So let's see if we can figure out how to do that. We have that script right there. Let's see if we can leverage that to make our scatter plot. Okay, we're not going to do any of that junk there. So we'll start to build our plot. So we need a square drawing canvas, and we want to plot S2S tuition versus 10-year salary. S and salary. That one, red marker, make it blue markers. Label build. X-axis will be annual dollars. Our Y label will be this in US dollars. We don't need a legend in this case because we're only plotting one series. And we need a title for the plot. Plot. Generate the plot, show the return. Save that, we won't need it later, no legend, no second plot. See what happens. So there is our annual tuition in US dollars versus salary after 10 years. So our highest value here is interest. Our highest tuition is actually producing the lowest salary. So it doesn't appear that there is much of a tuition prediction, but let's go ahead and make a model of this anyway. And we would do that using the same tools that we have up here. Not that one, we want to use sklearn because I think that's the easiest. So we just copy our setup script. Our predictors are annual tuition. The only predictor. And our response is salary. Done. Let's see what happens. Didn't get mad at us. Too mad. None of index annual tuition in the covariance. Oh, my bad. Not the name of the data frame, it says 2S. Okay, so it appears we have made a model. Now let's go to the fitting process. The fit, we'll scroll back up and initialize and fit a model. So we fitted the model and now plot the model on the data on the same plot. Now we will actually use our plotting routine. Get the labels correct. Get the data frame correct. So there is our model. It's a lousy model, but what do you conclude from looking at the model? Well, you would use that to answer these 3 questions. So if you want to learn more, there's some introduction to regression in Python, and there's some videos for those people that can't read. And the homework assignment is very similar. The only difference is you're using a different database. And here you have these things. When you complete these steps, double click these markdown cells to answer the questions that are asked. If there are no further questions, I am going to end the video and wish you all a great afternoon, and I'll see you on Wednesday. All right, everybody, goodbye. Have a good afternoon.